Hello, my wonderful pre-algebra students. Today we are going to start a little bit with systems of equations. You've actually been working with systems of equations. The zombie worksheet that we did had systems of equations, and I mentioned that, but I didn't really tell you what that really meant. A system of equations is just when I give you two or more linear equations, so straight lines, and we are only going to stick with two. When you're in advanced algebra, they'll maybe do more than that. But we're just going to have two equations. And you can see the example that I have here has two equations written. And what we're looking for is the solution, the one point that works for both of these. If you remember, when we graph a line, every single point on the line, that's why we draw arrows at the ends of the lines, every single point on that line is a solution for that equation. When I have two equations, I want to find the point of intersection. I want to find the point that they share, if they share any points. Sometimes when we write these systems, we might have a set bracket on one side like this. It's not always written like that. I just want you to be aware that it can be written that way. What we're going to be doing for right now is we're going to solve this with graphing. Eventually, there's going to be three different ways that we solve systems of equations. Graphing is the first way that we're going to use, and it's the first way because it makes the most sense for what we know. We know how to graph lines. Like I said, we've already done this. We're going to graph two lines, see where they cross. So what we do as our steps, we're going to graph both equations, find that point of intersection. Again, that's the one point that is a solution for both equations. That's what we're looking for. And then we can check the solution by substituting in. And don't forget, slope-intercept form, y equals mx plus b. The m is the slope, the b is the y-intercept. We've used this for quite some time now. So if I take a look at this first example, I have y equals 2x plus 3, y equals negative x plus 6. And we're going to try to clean that up a little bit. You know that when I have y equals 2x plus 3, that's really 2 over 1x plus 3. And you know that in the second equation, that's really a negative 1 in front of that x, and I can make that look like a fraction. So in the first equation, we're beginning at positive 3. That's what our b is. And our slope is 2 over 1. Up 2 over 1, it is a positive slope, so it should be going uphill. Or I can go down 2 and left 1. So here's my line. And the second equation begins at positive 6, right there. And my slope is a negative 1, so down 1 over 1. So when we graph these two lines and we look for that point of intersection, it's right here. That's the point that I'm looking for. That ordered pair is 1, 1, 2, 3, 4, 5. 1, 5 is my solution. Now, I can see it on the graph. I could also substitute that ordered pair, the x and the y, into my original equations. So when I substitute it into the first equation, 2 times, this is just going to be a 1. I guess I'm going to write this over here. The y is a 5 equals 2 times 1 plus 3. 2 times 1 is 2 plus 3 is 5. That one works. If I substitute those same numbers into the second equation, again, the y from my ordered pair is 5. There's a negative or a negative 1, and then I'm going to put my x in there as a 1 plus 6. Negative 1 plus 6, yes, that is 5. That works for both equations. So here is the work shown on, a little bit more step by step, and then my solution is 1, 5. That's how you check it. I know that not everybody checks every single solution, but that is how you can check to make sure that you've got the right ordered pair. In this problem, I've got these two equations again that I'm going to be graphing. I want to graph them, see where they cross, and then I can check the solution. So for my first equation, y equals x minus 1, or I can make my slope in there also. It's beginning at negative 1. My slope is positive 1, so up 1 over 1. So here's my first line. And again, you should absolutely be using a straight edge. Unfortunately, I can't on the board. For the second equation, y equals negative x plus 3, or negative 1 over 1, x plus 3. So I'm going to begin at positive 3, and my slope is negative 1, so down 1 over 1. So here's my line. That point of intersection is at 2, 1. And again, I can check that. There's my answer, 2, 1. I could substitute those x and y values into both equations to make sure that they work. And that's how you should, if you're ever unsure if you graph something correctly, just substitute it in and see if it works. In this example, I'm going to begin at positive 9 with my first equation, which is right there. And my slope is a negative 2 over 1, so down 2 over 1. Right there is my line. Let's see here. There we go. And my second line begins at 2. My slope is pretty steep. It's going to be 5, or 5 over 1. So up 1, 2, 3, 4, 5 over 1. I don't have room to do that again that way, so I'm going to go down 1, 2, 3, 4, 5, and left 1. So there's my graph, and the lines cross right here at 1, 7. Right, and again, remember, you can just substitute in. If I would put the 1 right here, 5 times 1 is 5 plus 2, yep, that's 7. And negative 2 times 1, that's negative 2 plus 9, yes, that is also 7. In this problem, that first equation looks kind of sparse. There's not a whole lot going on there. Remember, that's really y equals 1x plus 0. So we're going to start at 0, and we're going to have a slope of positive 1. So there's my graph. Second line begins at positive 1, and it has a slope of 2. So I'm going to go up 2 and over 1, which some people start to worry a little bit because actually my two lines are getting farther apart. But if I reverse, and if I go down 2 and left 1, still gives me a positive slope, but my lines do intersect that way. Ooh, and I missed my points a little bit there at the beginning. So that point right there is at negative 1, negative 1. That's not all. Do lines always cross? Is that always going to happen? Well, first of all, if the lines are going to cross, I will give you problems where you can find that. It's not going to cross like off the graph. So if you're working on a problem and you're like, oh yeah, the lines will meet eventually, there's something wrong. However, lines don't always cross. We have other options. Here's what they could be. Usually we get the one solution. On the left, that's what usually happens. You draw two lines, they cross at a point, we're done, boom, we're happy. The middle one, if we get parallel lines, I hope you remember what the word parallel means, they're never going to cross. And remember, our solution is the point of intersection. Well, if they don't have a point of intersection, there is no solution. And hopefully you remember, you can certainly use the words no solution, but we also have a symbol for that. No solution. In the last one, the two lines are off by just a little bit, so you can still see that there's a red line and a blue line. They are exactly the same line. This kind of problem gives us infinitely many solutions. Now, some teachers are fine with students writing the infinity symbol, and the infinity symbol looks really cool, and I love the infinity symbol. That's not actually the right answer. There are infinitely many solutions. You could write all that out, but what we're looking for is what those solutions are. It's not just any point anywhere. So you can't do like the fancy R, like any real number. It's not even numbers that we're looking for. We're looking for ordered pairs. So for instance, this point right here, not a solution. So I can't just say anything will work. However, every single point that's on the first line is also on the second line. So if it's on the red line, it's also on the blue line. So that's how I get infinitely many solutions. But what the solutions actually are is this. All points on the line. Every single point that's on one line is also on the other line. So when I'm looking for the solution for the system, it's every point that they share, which is every point on that line. So all points on the line. Sometimes students want to abbreviate that as APOTL, all points on the line. And I'm okay with that-ish. Please don't go to another class, another math class next year, say, Mr. Gagnon, this is APOTL, because he will have no idea what you're talking about. All points on the line. There's another fancy way to write that answer, but I'm not going to worry about that for this year. So here's an example. It's already completed. I've got both lines graphed. The first equation starts at 1 and has a slope of 3. The other one starts at -5 and has a slope of 3. You can see these two lines are parallel. This is a no solution kind of a problem, right? So we're going to use that no solution symbol. I want to point something out. The reason that I could tell by looking at this equation that this is going to be a no solution is because the slopes are exactly the same. Not that I have told you this before, but I want you to realize that if you have lines with the same slopes, they're going to be parallel because they're moving exactly the same way. They'll always stay exactly the same distance apart. So that's how I would know that those are going to be no solution. Here's the other situation. And it's kind of tricky to actually force this situation. My first equation is -2x plus 4. Y equals -2x plus 4. In the second equation, I would not try to graph that problem the way that it looks right now. We would say, oh, let's clean this up. Let's distribute that. So I would get y equals -2x, plus 4. Exactly the same as my first one. If they're exactly the same equation, clearly they're going to be exactly the same line when I graph it. So this would be all points on the line for my solution. All right, so a couple of quick examples. And again, hopefully you remember that tip that I just gave you. In this problem, do you see the slopes are the same? I can tell you right now, this is going to be a no solution. Please still graph it. You got to show me that you know how to graph those. So I would have, for my first equation, it's going to start at 2. I've got a slope of 1/4. Up 1 over 4. Up 1 over 4. Or down and left. Here is my first line. Second line begins at -3. Slope of 1/4. Up 1 over 4. Or down 1 and left 4. Right there. Never going to cross. They're all going to stay exactly the same distance apart. That is a no solution. For number 2, if they don't have the same slopes, it's not going to be one of our special cases. That only happens if they're exactly the same line, which would have the same slopes, or if they have the same slopes and different y-intercepts. This is just going to be crossing at one point. And in my first equation, I could put a +0 right there. So my slope is going to be 2 over 1. So up 2 over 1, or down 2 and left 1. I'm a little wobbly on the line, sorry. Second equation starts at +3. And my slope is 1 over 1, up 1 over 1. So you can see that my bad graphing skills without a straight edge didn't help me here. However, getting all of those extra points graphed did help. It was supposed to cross right here. So that would be at 3, 6 for my answer. Remember, you can check that by substituting in. In my first equation, the y was 6. The x is 3. 2 times 3 is 6. Here's 6. X is 3. That equation also works. And since we've done 2 of those situations, and clearly here's the 3rd one, you know that these are going to be all points on the line. When I clean up this equation, when I distribute this, I'm going to see that y equals 3x minus 3, exactly the same as this equation. I still should graph it. It starts at -3. My slope is 3, or 3 over 1. So here's my line. And my other line would be exactly the same. The solutions are all points on the line. Today's homework is the Solve Systems by Graphing worksheet. The answer keys in the Schoology. And again, if the lines are going to cross, they will cross on the graph. If they don't cross on the graph, check your work. See if maybe you graphed a positive slope instead of a negative slope, for instance. That's the most common mistake that I see. When you're done with that, there's a learning check in Schoology. On that learning check, I have 4 lines graphed, and I'm going to ask about solutions of different pairs of lines. So you have to be able to figure out which line is which with the equation to figure out which line you're looking at. And then you can just look at the point of intersection. So you don't need to actually have graph paper of your own to be able to graph those. If you need any help, let me know.